and you have the floor for the talk. Please come up.
Thank you. Thank you. It's really a pleasure to be here to talk to you today, because what we're talking about today is a huge subject, and it's such a big subject that NASA's not going to be able to do this on our own. When we're talking about how we address climate change, and then of course the main topic of our talk today, how do we get humans to Mars? This isn't something that NASA can do on its own. We want to do it as an international community, but even more importantly, we have to do it as an international community, because the cutting edge research into technologies and capabilities that we need to get to Mars aren't just being done in the United States. They're being done all over the world. So as we talk today about this journey to Mars, keep in mind that that first crew of international astronauts 20 years from now very well could be one of you. You guys are, some of you, or at least some of you, some of us are not the right age, some of you are the right age, to potentially be those first astronauts to Mars in 20-some years. Now, I could take all of David's time and talk to you about all of the cool science that we're doing right now at NASA. From studying the sun, this star that we actually do not have a great idea how it works. We monitor the sun with multiple spacecraft to understand CMEs, coronal mass ejections, these explosions that take place on the surface of the sun, sending particles streaming towards the Earth. And I like to tell especially younger kids, this would be a tragedy of epic proportions, because it could make your cell phones stop working. So understanding the sun on a practical basis to keep our electronic grid safe, to keep our communication network safe, and eventually, as we send humans to Mars, to keep our astronauts safe from these explosions of particles that happen from the sun, is one of the reasons that we need to understand our star. The second image there comes from the Hubble Space Telescope, which turned 25 last year, which is older than many of you in this room. In its 25 years, it has rewritten astrophysics textbooks in terms of our understanding of the formation of the universe, galaxies, stars, planetary systems. And it will be followed in about 2.5 years by our newest telescope, called the James Webb Space Telescope, that launches in 2018. And if you go onto the internet just in the past few days, it's in the clean room at Goddard Space Flight Center in Maryland, because they're attaching the instruments to it and about to begin a variety of tests of the entire mirror and structure. The mirrors are coated in beryllium and gold, and they're beautiful, and they have great live pictures that you can watch the construction of James Webb on the internet. In the center today, I'm going to be talking about some of the research that we're doing on the International Space Station every day. And if nothing else, the International Space Station, which people have suggested should win the Nobel Prize, is an amazing example of how you can get countries who aren't necessarily always having the best relationships here on this planet to work together in a cooperative fashion in space. So the space station is great on many levels, but to me, as an international diplomacy effort, it shows what we can do when we work to a higher purpose, like understanding our planet, understanding our universe. In planetary science, we have a whole fleet of international spacecraft that have been trying to understand our solar system. And I'm biased towards this because I'm a planetary geologist. I study volcanoes around the solar system. And we do this because we're trying to understand, how does the Earth work? How do volcanoes work? How does our climate work? How does our weather work? And by having multiple planets to go to where the conditions are slightly different, allows us to really get to basic understandings of things like climate. And that's obviously important, and I'll come back to this at the end of my remarks, to understanding our own extremely complicated planet. I like studying volcanoes on other planets because they don't have that pesky vegetation all over them. You know, our planet is like no other that we have found to date, in the fact that we have life, we have the oceans, and so trying to understand the complexity of all those systems. The US has 19 different missions right now studying the Earth in just about every wavelength, different repeats, to try to get at how do the fundamental interactions between the oceans, the land surface, the atmosphere, how does this work? How can we better predict what will happen in the future? You know, this is my favorite image that was returned by the Hubble. You've probably seen it. It's called the Hubble Deep Field image. We looked at the darkest part of the sky where there appeared to be nothing and just collected photons over days. And what did we find? So this is looking, you know, obviously the light is coming from further away, so you're looking further back in time, as closest as we've looked to the time of the Big Bang. And yet, even at that very early period in the history of the universe, we were shocked to see this much complexity. Each of those points of light is a galaxy, not a star. Each of those galaxies contains billions of stars. All this complexity, all this stuff so early in the history of the universe. What we are learning every day, what we will learn when James Webb pushes this time frame back even further, is stunning. My favorite mission that we've had over the last 4 years is a telescope called the Kepler Space Telescope. Kepler has been looking at a small area of the night sky, which might be hard for some of you in the back to see. It's those little white boxes on this image. If you went out tonight and you put up your thumb, you'd be covering about the area of the sky that Kepler has been looking at. And in that area of the sky, in its 4-year mission to date, it's found about 5,000 candidate planets around other stars. And because of the high resolution that Kepler's able to detect planets by the transit method, as the planet passes in front of the parent star, the light dims, Kepler's able to see it. Those planets have been in between the size of Earth and Neptune. Now, this is important because what we're looking for is another us. We're looking for a habitable planet around another star. And we have a bias based on what we know about the Earth, that that planet should be kind of like the Earth. Okay, is that great scientifically? Let's put that aside. But from our point of view, we say it should be a water planet because we think water is critical for life. It's a solvent, it's a polar molecule. So we say, all right, let's look for a water planet. So then we say, okay, that planet has to be the right distance from its parent star where water could be liquid on its surface. Kepler has found a handful of these potentially habitable zone planets. We're going to launch next year a satellite called the Transiting Exoplanet Survey Satellite, or TESS, and we estimate it'll find one potentially habitable planet a month for 3 years in its 3-year mission. The James Webb Space Telescope will then take some of those targets from both TESS and TESS and Kepler, and it'll start looking at their atmospheres, looking for things like methane, carbon dioxide, water, that would be consistent with habitability. Of course, then you'd love to know, are those gases changing? That tells you there's something dynamic happening on that planet, and could that dynamic thing be life rather than a volcano? I like volcanoes, but still, life would be better. But that's the kind of thing that we're looking for. And David will talk about what we'd like to do next, which is actually be able to image one of those planets around another star. But as we start to ask the question, is there life out there beyond Earth? What we really want to know is, okay, let's look at our own solar system and say, what are the chances of life beyond Earth? That'll help us when we're going out and thinking about extrasolar planets. Let's come back to our own solar system. Why are we the only apparently inhabited planet in this solar system? That makes Mars our prime target to explore. And I'll come back to Mars in a minute. But we actually have a few other places in our solar system where we think there's actually a chance for life. Now, these are not in the habitable zone. I just told you, oh, we're looking for planets in the habitable zone. These places are not in the habitable zone. Europa, in the upper right, moon of Jupiter, Enceladus, moon of Saturn in the bottom, and Titan, another moon of Saturn in the upper left. Now, as you probably know, both Europa and Enceladus have icy crusts, but beneath those icy crusts is a liquid water ocean. At the base of that liquid water ocean, we think there could be volcanic activity out of the rocky core of the planet. Now that's important because it's feeding nutrients, potentially, into that subsurface ocean, nutrients that life could use. Now, how do we know this? Well, for Enceladus, we actually flew the Cassini spacecraft right through those water plumes. So we know they're water. We know there's silica coming out of them, which seems to be indicative of that volcanic activity, so that's good. We've also found organic molecules. But our mass spectrometer on Cassini wasn't good enough to tell us what those organic molecules are. All we know is that they're there and they're potentially big. So we need to go back. But first, we want to go to Europa. The Europeans have a mission called JUICE that's going to fly in the late 2020s, and the US is working on a mission also that would potentially have an orbiter. So really intriguing targets. I don't have time to talk about my favorite place, which is in the upper left. That's Titan. It's a moon of Saturn. It actually has seas of liquid methane and ethane, and that bright spot you see at the top is sun glint off of a Titan sea. No water, very cold, 90 degrees Kelvin. Could you have life? Maybe, maybe not. We'll never know unless we go. But Mars is our prime target because we've landed now 8 times on the surface of Mars. The international community has sent all these rovers, orbiters to Mars. What have we been doing with all that data? What we've been doing is trying to figure out the history of water and the conditions on the surface of Mars. And what we've learned is that about 3 billion years ago, early in Mars's history, probably when it had a magnetic field that would have protected the surface from incoming radiation, Mars had a liquid water ocean on its surface. Okay, around the same time life evolved on Earth. Life here evolved in the oceans, and it stayed in the oceans for about 1 billion years. So those same conditions existed on Mars. So could life have evolved on Mars? Why wouldn't it have if the conditions were so similar? But after 1 billion years, Mars, or earlier than that, Mars lost its magnetic field. Atmosphere was getting stripped away by the solar wind. Mars lost a lot of its water, the rest retreated underground, got very cold, inhospitable, radiated surface. Any life, did it go extinct or did it go underground? We don't know, but it's probably never got very complex. So when we're going to Mars and finding life, we're not looking for dinosaur bones. We're looking for fossil microbes, so this is not going to be easy to find. So I have a bias that it's going to take field geologists like me going to the surface of Mars, cracking open a lot of rocks, having a laboratory on the surface to not only determine was there life on Mars, but what can we use about that life to help us understand life here on Earth? Does it have cell structure like ours? Does it have RNA, DNA? These are the questions we want to answer, and frankly, robotic spacecraft, I think, are going to give us strong indications of life, but the scientific community, we don't actually like to agree with each other. We like to argue. And so for that definitive evidence of life, I think it's going to take humans. And that's hard, and David's going to talk about how hard it is. But the first step to getting humans to Mars goes right through the International Space Station. It's the only place we have where we can figure out how do we keep humans healthy for that 8-month trip to Mars, 8-month trip back in microgravity. How can we test the capabilities we need for that long voyage? The ISS is the place to do it. Now, in the past year, we've had what we call the 1-year increment. We had 2 people in space for 340 days. Okay, it's not quite a year, but whatever. Scott Kelly, who's an American astronaut, Mikhail Kornienko, a cosmonaut. And what's better, Scott Kelly has an identical twin brother, Mark Kelly, who used to be an astronaut. So not only could we take our normal 6-month astronaut stay, extend it to a year, and try to figure out what happens to all those things that happen to you in space. Muscle wasting, bone density loss. What happens when you go from 6 months to a year? And also, by the way, we now have a genetic control here on Earth that we can help analyze. What we're trying to do is develop mitigations to all the health effects that happen to you in microgravity. For example, it turns out if the astronauts exercise for about an hour and a half every day, which of course all of us do every day, right? If the astronauts do that, they actually come home with about the same bone density as they leave. So as an international community, when our astronauts all go up to the space station, we are using them to help understand how to get humans not just to the ISS, not just to low Earth orbit, but out to the vicinity of the moon, and then eventually to Mars. And again, sort of minimum 15, 18-month trip, long time in microgravity. We do a lot of other research on the space station. David will talk about some of the things we're doing to get technology ready, but I just want to mention some of the things that we're doing. For example, food. We've got to keep the astronauts eating food, right? We do fundamental physics, things like look at dusty plasmas, a cold atom lab. We grow very large proteins that help us to look for new drugs to treat disease, and we can test new technologies like a bone imaging spectrometer. Now, we also have been using the ISS as a platform for Earth observations. All of you well know, this is just binned surface temperature data, deviation from average surface temperature. This is data, this isn't a model, for the 5-year period from 2010 to 2014. No surprise to you that the Earth is warming up, and in fact, obviously, even the first 3 months of this year were alarmingly warm. 0 degrees centigrade this Christmas at the North Pole, shocking. And we see the effects of human-induced climate change in places like Greenland, where we're losing massive amounts of sea ice. We estimate from the sea ice we're losing from Greenland and from Western Antarctica an additional meter or more of sea level rise, more than what was estimated in the original IPCC reports. So how can the space agencies of the world help? Well, we can use our data to help address a number of different areas across the globe that as the climate changes, we get more severe weather. Ecodiversity is changing. It's harder to grow crops in some places, easier in others. So we can use space-based Earth observation data to help mitigate the effects of climate change, make countries more resilient against climate change, while at the same time bearing witness as to what's happening. So value from space to people here on Earth, as well as value in getting humans to Mars, which David is now going to explain how we're going to do this.
So Ellen and I were trying to figure out what kind of slide would be a good transition slide, and we chose the nighttime side of Saturn as a good one. And it's for several reasons. One is it's science that really guides exploration, and it's technology that makes it possible. So I encourage you as you're studying here, if you're a technologist or engineering, that you find people in the science area to collaborate with, because it's important to have that partnership. Second reason, it's just beautiful. And I don't think we really expected that to be as impressive. You know, we'd always seen Saturn from the lit side, the sunlit side, but then very impactful when you see it from this side. The third is, we're all in the photo. Can you find us? That's right. Now, I don't know where you're pointing. But in the bottom left, just outside that hazy band, that's Earth. So it sort of gives you some perspective, just like the moonrise on the Apollo 8 mission gave us perspective about Earth. This even gives you more perspective. So I think this is a great slide when I saw it when I got to NASA, and this shows all the stuff that's flying, and or at least in formulation, and is going to fly very soon. And it shows the 4 areas of science that that Ellen talked about. Starting in the upper left, those are the spacecraft, and almost all of these are international missions. I think over 70% of them. Upper left are the Earth science missions. Upper right are astrophysics. Bottom left are heliophysics. And bottom right are planetary, with a nice little inset for Mars. You can really tell that Mars has been our focus for decades now. Of interest to me, I grew up thinking Voyager was a planetary spacecraft going through the Grand Tour. Oh, thanks. And then I realized on this chart, as I'm looking for Voyager over here, it's sitting over here. It's actually now at the it's beyond the heliopause, and which is the demarcation between where our solar wind dominates over the interstellar wind, and it's now an interstellar spacecraft studying the edges of the influence of the sun. So I want to tell you a little bit about some other mission directorates in NASA. This is aeronautics. There are a number of demand signals we're seeing, demand for increased air mobility across the world, the environmental challenges from energy and climate sustainable travel, and also a convergence of a number of technologies in control and information technologies and communications so that we can lead to autonomous air operations that still has safe operations. So this has led to a number of areas we're investing in, such as innovative commercial supersonic aircraft, low carbon propulsion, some ultra efficient commercial vehicles that get specific fuel consumption, not just improve it by a few percent, but tens of percents, and assured autonomy for transformative aviation. Another mission directorate is our Space Technology Directorate. Hopefully some of you can identify your research here. We have 8 main themes. I'll mention a few: in-space propulsion, optical communications, entry, descent, and landing systems. It's very hard to land on Mars. The atmosphere is so thin, it doesn't really decelerate you very much, but it's thick enough that it heats you up a lot. So thermal protection systems. How do you slow down when you really can't get a good grip on that atmosphere? Lightweight systems, also observatories, and I'm going to talk about some of the technology that allows us to characterize exoplanets and image exoplanets at the end of my talk. So now I want to focus on the 4th area, which is human exploration and operations. However, we really see that as an agency and international collaboration. It's not the mission of one directorate. It's not the mission of one space agency. We cannot do it alone. We need help from all of our space partners, including all of you in this room. So we see this really at the convergence of science, technology, and human exploration, and we see executing it in 3 stages. The first stage is the one we're in now, roughly this decade going into the 2020s, and that's where we're using station to develop the technology we need. We're also developing launch systems, both in the commercial arena and with the SLS, or the Space Launch System, and the Orion Crew Module. The second phase is where we're going to move out to the moon. We call this the proving ground, where we're going to go into lunar orbit and show that all the tools we're developing now actually work for the duration of a human mission to Mars, which is roughly on the 18 to longer months, but it's up to 2-year mission. So we're going to prove that works there. Also in the proving ground are these robotic missions up there. We've been exploring Mars since the 1960s. But in the next decade, we're going to have to start answering questions that not are only for science, but are also enabling for human exploration. So we're starting to formulate what those missions will be in the 2020s and how we're going to partner with the international community. The last stage, the 3rd stage, is to take humans to Mars. It's going to start with a free return flyby of Mars, then an orbital mission, then a lander mission. And when we start landing, we want to land for the next several missions at the same place. So each mission we take can put down infrastructure that will make the next mission easier to do. Our intention is to go to stay. So robotic exploration of Mars is hard. This graphic, I think, is a great way to show it. Starting up here in the 1960s all the way down to the present, these are the various attempts that we have made to explore Mars, either from on orbit or landers. And what you can see is the reds indicate failures. We've been getting better. Hard work pays off. We're now we've flown by Mars, we've orbited Mars, we've landed on Mars, we're roving on Mars. If you were arriving in our solar system today and you happen to fly by Mars, which would probably be a good idea, You'd almost think that it's populated with a bunch of thinking machines, but it's populated. It would be very interesting. And this is what it's populated with. We have orbiters, we have landers, we have some of those are rovers. These are international missions. We're answering the questions that science poses. Look for the water, find locations of habitability, and then search for signs of life. So by doing these robotic missions, we've learned a lot. We've learned a lot about the orbital environment up here on the left. Learned how to do gravity assist maneuvers, aerobraking, deep space navigation and communications. We need to use that to get to Mars. We've also learned a lot about the atmosphere, about how to land through the atmosphere, the intensity of storms and density and composition and variability of the atmosphere. These are things we need to get to Mars. We've actually, with the Curiosity rover, how many people have remember the, 7 Minutes of Terror? Oh, come on, shy crowd, come on. I'm a professor, I know how this works. We landed 1 metric ton. We're gonna have to land a lot more than that. We need a lot of smart minds thinking about how to do that. We've also learned a lot about operating on the surface, but there's still a lot more we need to learn. And that's why we need to continue this robotic exploration in the 2020s. Human exploration of Mars is hard. You know, I keep saying it's hard, so, you know, is it too hard? Well, this was a little bit before my time, but President Kennedy said, we do these things not because they are easy, but because they are hard. That's the end of the quote, I think. But then you know, it's because when you do the hard things, you don't make incremental improvements, you make revolutionary improvements. You know, computers, global communications, advanced materials and alloys. These would have eventually happened. But what Apollo did is it pulled a decade out of the 21st century and moved it into the 1960s and really accelerated that technology. And it didn't just benefit and inspire us, but it really impacted the economy, education, and all that. All that's important. So we have to put a lot bigger payloads on the surface. We have to launch more often. We have to deal with the dust. If you ever see the photos of the Apollo astronauts after a moonwalk, they are filthy. They are dirty and covered with dust, which is actually sort of a glass that is dangerous to breathe. But new here is we have to start operating on these spacecraft without direct and continuous or instant communication with mission control back on Earth. That's an interesting twist. Finally here, if we're going to stay, we can't just keep shipping supplies. We have to start figuring out how to use what we find, the water, the atmosphere, to make fuel, to make water to drink, to air to breathe. So these are nice view graphs with some photos and things, but it's really happening today. We have a very energetic commercial industry developing launch capability. Anyone heard of SpaceX? No, yes, no. Blue Origin, Virgin Galactic. I mean, it's the Wild West right now. And it's very exciting. And NASA's figuring out how to work with them. There was an announcement yesterday, or 2 days ago, I've lost track of time, okay, where SpaceX said we're going to Mars in 2018 with their Dragon module, and the program's called Red Dragon, without a crew. But they're going to attempt a soft landing on Mars, and NASA came out and said, and we're going to help you because we're going to assist with navigation and communication and some of the EDL technology, or entry, descent, landing technology. So that's very exciting. You know, we have to land larger payloads. They want to make the attempt. We're all for that. We're going to help. There are 3 companies now that are working to supply space station with cargo. There are 2 companies working to launch crew to the International Space Station. First launch is planned for 2017. We are building the Orion capsule up here. This is the service module that goes behind it. This is being provided by the European Space Agency. Thank you. And these are other elements. We're putting all the pieces together. It's being built today. It's not just view graphs. Here's the SLS. Here are adapters, engines, upper stages, the launch tower and all that. It's all coming together right now. First launch in late 2018. So here's the first configuration of the SLS. Here is the ESA provided service module. Again, thank you. This configuration should throw 70 metric tons in the low Earth orbit, though it's not going to stop in low Earth orbit. That's just sort of a way to measure its capability, which is a lot larger than the current expendable fleet. So the first mission with that in 2018, which will not have a crew on board, is to go out to the vicinity of the moon and orbit. And at a high energy orbit, means a high altitude. That has several advantages. One is that it's a stable orbit where you can put the pieces together before you head to Mars. The second is we can use the moon's motion as a way to gravity assist or slingshot us to Mars. It's free propulsion. Third is it's a place where all the latitudes on Mars are easier to access for those that want to go robotically and with humans to the surface. So when we get to Mars, there's a whole bunch of stuff we have to do. We have to land. We have to have, I already talked about how difficult that is. Some of these are inflatable shells to get a bigger surface area, get more drag. We have to work on the surface, have a home, have robots and humans working together, power systems. We have to get back off the surface. That's a challenge. And start developing higher bandwidth comms so that we can all watch it on TV or on the computer. Geez, I just dated myself, sorry. All these things are being built right now as well. These just show some examples there. Here's the solar electric propulsion, which is high efficiency. This is high fuel efficiency. It takes longer, but when you want to move cargo out in advance, it's a good way to do it. You could actually think some of these are cyclers that move between the Earth-Mars system. The eventual goal is this. Basically, we, in the mid-1990s, we had our first little rover on Mars. Then we moved up to the Mars exploration rovers. Then Curiosity, now Mars 2020 is the next. And we want to get to the ultimate rover, the ultimate smart rover, and that is the field geologist that has high mobility. This is Ellen right there. So just because the productivity that the human can do at the site. So let me now transition to some of the technology to detect other worlds. In 1996, there were 9 planets. Later, we demoted Pluto, but we still love it. We went there. And now we know about 5,000 of them. That's amazing. That's going to grow exponentially. I mean, probably faster than that, I don't know. But it's amazing. So the problem is, you got this really bright object, you're looking for a really dim object, somewhere between 1 million and 1 billion times dimmer, depending what wavelength. So the trick is, you got to block that light so that you can reveal that planet and now characterize it. 2 ways we're looking at. One is internal coronagraphs. These are sort of diffraction masks that are able to spread the light in different directions, so you can make these very dark regions in here where you can close in there with less jitter than me in order to identify those planets and be able to look at their spectra. And the other method is to put up one of these star shades which can block the on-axis light, and so that you can see the light from the planets coming around it. This is not to scale. This distance from here to here is tens of thousands of kilometers. So this is only about 20 meters in diameter, so don't be fooled. There's a bunch of challenges with the coronagraph inside. We get high contrast, deformable optics, post-processing. We have to get high angular resolution, or fine angular resolution with large optics. We have to make sure this is stable by doing wavefront control, and we have to have very sensitive detectors to see the signature of those planets. For the star shade, there are equally challenging problems. We have to suppress the light by developing a very accurate shape pattern here. For those who study optics, you might recognize that pattern. I don't. But we have to do formation control, because remember, that arrow is tens of thousands of kilometers apart. And we have to deploy these large structures very precisely. So I want to leave you with this slide. This is an artist rendering. Hopefully someday we'll see this, but this is an artist rendering of what an exoplanet, an Earth-like planet, an Earth 2.0, a pale blue dot might look like. But the thing is, we are right at the cusp of some very exciting discoveries. Trying to answer the question of, are we alone in the universe? How many planets are out there that other Earths? We're right on the cusp, and you're right at the point where you could really be answering those questions. So I'll leave you with one final thought. You know, this is your space program. Get involved. You got to grab it, you know, by the lapels and provide your intellect and your passion to it. So I urge you to do that and do it every day. Thank you.
Thank you very much. I think it's time for questions. Are there any questions? Of course. Yes, please. Please come up.
So I have a question about sending humans to Mars, and you mentioned that unlike the Earth, Mars doesn't have a wonderful big magnetic field which protects the surface from the radiation from the sun. So of course a big problem with sending humans to this is that they're going to be bombarded with all of this solar wind and the solar radiation. So what steps, what's happening? Are they thinking, hey, let's create a magnetic field, or let's use material science to create a shield? What's happening with that?
Maybe this one better.
Oh, okay. So that's true. Astronauts, once they leave, in fact, once we even get out to the orbit of the moon, you're subjected to both solar radiation and cosmic radiation. Solar radiation is something we actually know how to deal with fairly well. You can shield against it because the particles aren't coming in at too high a velocity. So for example, on the International Space Station, we have an area that the astronauts retreat to when we know there's a big blast of incoming solar radiation. So while it's not trivial, it's something that we feel through materials and everything else that we can reasonably protect the astronauts from solar radiation. I will say we also had an instrument on board Mars Curiosity that on the way to Mars and on the Martian surface has been characterizing the radiation environment, so we do actually have some data to work off of. On the way to Mars and on the surface of Mars, it's actually cosmic radiation that is the thing we really worry about. Those particles are coming in at such a high rate of speed that they're very hard to shield against. Metal doesn't work. They energize those particles and they all come cascading towards you. No thanks. You know, maybe we can use water. We've thought about that. So what we've also done is we've worked with a lot of research that's been done, and we've worked with the Institute of Medicine in the United States. And what we've been looking at is the amount it would increase your lifetime cancer risk. And right now, while it raises it above, say, what would be acceptable for somebody working in a nuclear power plant, at this point, we've determined that it's more an informed consent issue. When you think that we're not going to be doing this for some time on the future and how much we're learning, for example, some people are better repairers of radiation damage than others. Can we use that information to find countermeasures that can help protect the astronauts? So we're looking into that. We're also looking into the issue of generating magnetic fields, but the problem is you need such a high power field, high energy field to deflect those cosmic rays that it's not, at least it's kind of something way out there.
Thank you. Any other questions? Please, over there.
You can shout.
Get another mic up to another person.
Yeah.
May I ask one most important question between? When do you think will this most sophisticated rover with the 2 legs be up there on Mars?
You know, right now, we're targeting the early 2030s for that first mission, but that's going to be more of a fly around in an orbital mission. We haven't determined that yet. I think it'll take to the late 2030s, early 2040s to actually get humans landed on the surface. But right now, we don't really want to pin that date down because things are changing so rapidly. Technologies, what do we do with entry, descent, and landing? And frankly, when you see things like Red Dragon happening, what role will outside players play in either keeping that date where we think it might be or moving that date forward this way?
So you don't have a detailed roadmap?
We're working on a detailed roadmap to get us to the early 2030s and the technology development roadmap to get us further. But frankly, because we're then talking about 20 years from now, you hate to pin yourself down to a single path.
So let's agree, if you know more, please come back to us and tell us, okay? So, please.
We are working on.
Could you repeat because the speaker didn't work?
Are we working on nuclear thermal propulsion, and what's the status of our work? And so first I'd like to say we invest across the spectrum, what we call technology readiness levels. So there's the things we'll need tomorrow, then the things we'll need the missions after that, and then in the future. One of the nice advantages of nuclear thermal propulsion is, remember when I talked about solar electric propulsion? It's lower thrust, it takes longer to get there, but it's highly efficient. Nuclear thermal propulsion is highly efficient and high thrust. It could really be the way to cut the duration of the trip out to Mars and back by a lot. There are a lot of challenges with it. There was a fair amount of work in the 60s in this area, but there's always concern about launching highly enriched fissionable material. There's a lot of thermal problems to try to figure out. We are working on right now for power, some sort of 10 kilowatt kind of fission reactors that could be useful on the surface. We're also looking at the possibility of having lower enriched uranium systems for fission, because they're probably going to be easier to launch and safer, but it's still a big challenge. And it's one of those technologies that we're not going to use on the first few flights, but we want to design the system so that as they become mature, we can take advantages of new technologies and bring them in and use them for subsequent missions.
Any other questions? You want over there.
You mentioned a return trip a few times. I've heard of a few Mars missions that were suggested. I think it was Mars 1, where you send just people to Mars and you leave them there. I wanted to ask if, okay, that sounds kind of mad, but...
Are you ready to go?
Well, if you supply me with sufficient ways of staying there, of course.
Good point.
Sign me up. But I wanted to ask if there's an opinion of NASA or international opinion about those kinds of missions.
Yes, we are going round trip for several reasons. We think the first few missions are exploratory in nature, so it's very difficult to be able to sustain the life of the astronauts on that planet for the rest of their lifetime, or natural lifetime. Forget how I ask Alan to define that. But something if you ever get a chance to talk to an Apollo astronaut, they say that spent 2 days walking around picking up rocks on the surface of the moon, but I spent 50 years talking about it. And that ability to come back, which the rover doesn't have, the ability to come back and speak your language rather than ones and zeros, speak your language and help you feel like you actually were on the moon with that astronaut. I think that's pretty impactful. It's inspirational. A lot of the astronauts retire into universities and bring that passion to the next generation.
Yeah, and also think about the fact that Mars isn't Antarctica, and you think of what a hard place it is for humans to live in Antarctica, and Mars is not like that. And you can't breathe the atmosphere, radiation issues. The soil is full of some chemicals we found called perchlorates that are really hazardous. So it is not easy for humans to live on Mars. So I like to think of it more, we'll have a base camp, we'll have a scientific lab, but in terms of humans going long-term to stay, that's really pretty difficult if we want to keep people alive, which is a goal.
What role do you think will the commercial sector maybe play in the road to Mars, especially since the announcement yesterday that SpaceX might go ahead and land on the surface even in 2 years? And do you think that this could maybe accelerate the plans to land there?
When you look at how NASA went to the moon, we did it as a US government thing, race kind of atmosphere. I think going to Mars is going to be entirely different. We're here talking to our international partners. We want this to be international. We want all the nations of the world that have space agencies participating. And I think the commercial sector is going to play a significant role, and obviously it's nice that we can talk about Red Dragon, because I think it's a really important step. If we can, if SpaceX can help work on some of those EDL technologies that we keep saying are so hard, NASA can spend its money doing something else. And so to me, the journey to Mars is all about partnerships. And the challenge that David and I have been working on over the last year and will continue to work on is, how do you have a 15, 20-year roadmap that is flexible for change? And not just who are you going to partner with, what new partners are going to come in, what technologies are going to be developed, who's going to back away, how is your funding going to change? So you have to have a resilient set of architectures that allow you flexibility. So if things go well, hopefully all those dates move towards us. I want to see humans walking on Mars in my lifetime, but maybe if things don't go so well, your plan has to accordion outward a little bit.
I like to think about it like the ocean explorers. Let's take Magellan. Now, I'm an engineering major. I'm probably going to mess up my history here a little bit. But so Magellan headed out of some port, and you know, at the edge of the harbor, exploration started. But that harbor was probably not, the docks were not built by Magellan. The ship probably wasn't built by Magellan. The roads that brought all the cargo and the crops wasn't built by Magellan, and the crops weren't raised by him. There was a commercial or something like that entity that provided all that, and he took advantage of it. So during Apollo, that interface between commercial and exploration was on the ground at the Kennedy Space Center. What we want to do now is start pulling that edge of that harbor up into low Earth orbit, eventually into lunar orbit, so to make the harbor at the edge of the Earth-Moon system, and then just keep pulling it out, because we can't support through exploration funds that whole supply chain all the way along the line, and commercial is key to helping us explore.
Do you expect any consequences on the current NASA programs with a potential election of President Clinton or President Trump?
Yeah, thanks, David. You know, NASA is confident that we have a good plan. We think this is a compelling plan. I would say the fact that we all got you all to come out here on a Friday afternoon shows that this is a plan that the public thinks is intriguing, that it's interesting, that it's something that the people of not just the United States, but people around the world think, this is something we can do. This is something hard, but let's see humans move onto the surface of another planet in our lifetime. And I think it's that compelling nature of this journey that's going to carry it through what will be changes in politics, changes in budget situations. The advantage that we have right now in the United States is, I mean, I'm sure you've heard our two parties don't necessarily get along so well. Our budget has actually in the last 2 years increased in a time when, just like all countries around the world, there's a lot of pressures on international governments on their budgets. NASA's budget has increased since we've been articulating this plan. We have bipartisan support from both parties, so we are fairly confident that despite an administration change, the fact that both parties in Congress are very supportive of what we're doing is going to carry us forward, and we're going to continue to make progress on this.
You know, I talked about the 3 stages of the journey. We're still in stage 1 here, working at International Space Station and so forth. I like to sort of look back at the Apollo era and say, right now on the journey to Mars, we're kind of where we finally got people in the low Earth orbit. Yuri Gagarin went up, you know, Alan Shepard, John Glenn went up, and we're saying, yeah, at the time we were probably saying, I wasn't in the conversation, but we were probably saying, we're going to do what? Land on the moon and come back, you know, within what time frame? So we're at that same stage. And, you know, I think we could easily be questioning ourselves about our ability to pull this off. And I think really the largest challenge is if we can maintain focus and a certainty of purpose and get this job done on the international scale. After we accomplish this journey, I think we won't even recognize ourselves anymore for how much we've been able to do.
What's the role of the moon on your road to Mars?
Well,
Both scientifically wise and also
so I mentioned the technical issues. Free propulsion, that's invaluable. So the ability to slingshot there. But there's another one. There are other spacefaring nations that have goals to go to the moon, and we are eager to help them achieve their goals so that they can help us achieve our goals, or hopefully our mutual goals. And if there are countries that want to land and humans on the surface of the moon, we're happy to help them to get out to the vicinity of the moon. Our next goal is to put out a habitation systems in orbit around the moon, be a great staging location, and as I said, it would allow you to access almost all latitudes at the moon. So we're here happy to help. We'd ask that when you build that lander, can we have one of the seats just to take the ride?
As a test bed?
Well, we have to look carefully. When we look at technology investments, it's important not to just work on technologies that are focused on one location. You can't do this for everything, but it's important to take a look. Is there a technology like the chemistry of the descent and ascent engine? Is there a chemistry that is useful at both locations? Obviously, heat shields and parachutes aren't very useful for getting on the moon. But retropropulsion, we're going to need that on Mars. And so if there's some elements here, whether at the vehicle level or at the technology level, which is destination agnostic, or that is useful in multiple destinations, and that usually involves a compromise. If that compromise is not too severe, then that's worth an investment.
Any other question over there?
So in America's last big push to space, there was quite a us versus them mentality with the space race and stuff. From a PR perspective, how do you plan to build up the hype and kind of get that optimism without necessarily such a confrontational mentality, I guess?
I think to keep the public coming along with us, which is something that obviously we need and we want. I think first of all, you get them involved. You find ways to say, how can we take the energy and smarts of people around the world to help us get to where we want to go? So I'm a huge fan of citizen science, crowdsourcing, figuring out how we can use the power of the hive mind to help us get to where we want to go. The other thing is, I think you have to make steady, sustained progress. You have to make people say, yeah, they're doing things. So I was really worried about this, and then I started writing down all the things, from our robotic missions to Mars. 2018, we're going to be launching InSight. ExoMars rover is going to go. Later that same year, we're going to launch the unmanned SLS in Orion. 2 years later, we're going to have another rover at Mars. Then we're going to have the first crewed mission go out to the vicinity of the moon. Then we're going to send another mission to Mars. And then, things are going to start. We're going to be making steady progress. So this isn't going to be, we're going to be sitting around until the early 2030s and we send humans. Right now, NASA just announced we're looking for ideas for habitat, which will be the Mars transfer vehicle that will be what the astronauts go in from the moon to Mars and back. We've got industry, our partners are looking at that. What would that Mars transfer vehicle look like? We hope to start testing that out in lunar orbit in the mid-2020s. So we're going to be making progress. We're going to have people up in space working towards this goal. So I think there's going to be enough going to keep the public engaged.
There's also a strong economic argument. The United States estimates that every dollar it spends on space activities reaps about $4 in return to the economy. There's also secondary markets that are created. When we develop technology for space, we find other areas that are non-aerospace where that technology is very valuable and companies actually develop business cases around it. I'll give you a few examples. The camera, anyone have a smartphone here? Anyone? That little camera, which is gives you unbelievable quality in a very small package, that came out of the miniaturization of camera systems in spacecraft. There's a nutrient that was developed for astronauts, which is now in 95% of baby formula worldwide. There's a whole bunch of these. There's space-acquired data, Earth observing data, which is being used to find aquifers, and it has a 98% success rate, which is amazing. That, to have that level of confidence when you drill, especially during a humanitarian crisis and you need water now, to know that you drill in the desert and there's going to be water there, 98% likelihood. That's amazing. So you got to communicate all of that out there. There's also a leadership dimension to this. You know, I think of Europe as the leaders in exploring the oceans. You taught us how to explore. And space is a vast ocean, even larger. And Europe should have a leadership role in that exploration. And leadership is important. Otherwise, we don't know what to do.
One final question, please.
I have a question regarding the distant future of human presence on Mars. What is your idea or your opinion on terraforming? Do you think it might one day be possible to create Earth-like conditions on Mars, or are there studies happening at NASA right now?
Ellen has a great answer, so I'll go first. Well, you know, it has to be if we're going to even consider it, it has to be in the distance, because a really impactful question to humanity is, are we alone? Did life actually start elsewhere and not just on planet Earth? So we want to make sure that when we go out there, we find it. That would be useful if it exists, or if it existed, we find the evidence in the fossil record that it existed. So we want to be careful not to start digging up the dirt or too early.
But there have been academic papers that have been written on terraforming, so it's, you know, obviously theoretically it's feasible. The problem is the timescales that have been suggested, for at least ideas we have on how you would terraform, are quite long. But I have a strong bias that, you know, we should focus that sort of attention on cleaning up the planet we've already messed up, rather than going and altering other planets. So.
So thank you very much. Let me ask one final question. I didn't see any single slide about ARM, Asteroid Redirection Mission. So did you cross it out already?
It was actually on the slide up there that had the science, technology, and human spaceflight on it. You know, we have to find, before, I talked about the proving ground. We have to prove that the tools we need are going to work all the time when we need them when we go to Mars. So that's a mission where you could demonstrate that some of the technology we need does work before we actually have to rely on it. And so things like solar electric propulsion is something that ARM could mature. Robotic manipulation, proximity operations around another object, in this case a natural object. You know, there's a bunch of technology there that can help. So it's.
So thank you very much again. As you saw, we are on the road to Mars and to the other planets. So please again, give a big applause to both of them. This was an applause to see you back in the near future, whatever that means. Thank you very much.